And I want to talk a little bit today about 3D data and different perspectives on quantity and quality for perception-based kind of tasks in 3D. So we've all seen this kind of remarkable progress that has been made in terms of text and image synthesis, being able to generate practically almost natural sort of realistic text with ChatGPT, and then Stable Diffusion, and now many other state-of-the-art models can generate an incredible fidelity in terms of images. And this has been driven by not only sort of architectural and learning-based kind of design advances, but also by the massive quantities of data that's available in the 2D and the 1D kind of domain here, where obviously training on billions of training samples, if not more, certainly allows for learning a very powerful landscape in these domains. So of course, this brings the question, can we do the same in 3D, or can we leverage this kind of information in 3D where we have this extra spatial dimension? And, is video maybe enough to give us signal on 3D data? Because certainly video, there's a lot of it around on the internet. But in order to get a 3D representation, there's a couple of challenges there that are still yet to be solved in terms of reliable camera pose estimation on sort of in the wild videos like those on YouTube. Structure from motion is challenging to actually reconstruct a 3D representation from the video, and it would be rather appealing to be able to do so because the 3D representation itself allows for direct spatial queries if we want to do something like have a robotics-based task that a robot is able to navigate around, manipulate different kinds of objects, and interact with the scene. It helps a lot to have that natural 3D representation here. So there's also been a remarkable amount of progress in video foundation models these days, and they produce an incredible quality of output videos under sort of relatively short time durations. But I don't think this is enough for us to capture that real 3D representation here. I mean, in particular, the scene representation that comes out is just not an inherent spatial representation, right? So you cannot go through and interact or reason about editing and provide direct spatial queries in these kinds of models. And inherently, from a slightly different kind of perspective, this kind of learning through images or through video kind of representations is inherently less efficient than learning on an equivalent amount of samples that have the 3D spatial information, because you have to relearn certain kind of concepts that you get in a 3D-based representation, which is that of view consistency, temporal consistency, and so on. And so that will require inherently having more data samples that are needed in order to effectively train these kinds of representations that don't have a direct spatial information here. So if we look at 3D data, there's a strong sort of quantity quality kind of potential trade-off here, where you see that in text, images, and videos, you have, at least in terms of public data sets, very large quantities that are available. So, tens of millions, if not into the billions kind of range. And we do now start to see data sets of reasonably large scale for individual 3D objects like Observerse, and 3D scenes is already dropping several orders of magnitude down in terms of the amount of data that's available here. So certainly in terms of the sort of quantity quality trade-off and capture, large scale 3D in terms of quantity is a lot easier to capture if this can be done through commodity sensors, like with an iPhone that most modern iPhones now have a LiDAR sensor that allows for 3D capture. So there's a large potential for such kind of large scale 3D capture, but of relatively low quality. And I think something that we've learned from seeing these developments also in the text and image space is that quality is actually of a pretty strong importance in terms of the ability to learn effective representations here. So the hope is also that if we actually learn 3D representations, maybe we can have more efficient kind of learning paradigms. So when I started kind of in this space, I was working on 3D reconstruction, so real-time reconstruction of indoor environments, and then also their semantic understanding. And we built a data set based off of the reconstruction methods in order to be able to annotate semantics, to provide some data for driving 3D learning kind of methods. And this is kind of interesting. We originally charged out all of the annotations on Amazon Mechanical Turk, and it was okay-ish. But in the end, I actually did most of the fix-up of all of the annotations on the 3D scenes, and you can see that the quality there is kind of okay at best. You get the sense of what's the general kind of semantic breakdown. Certainly the geometry quality is limiting the annotations, that you don't get sort of these perfect semantic labels. And in fact, despite that, one person ended up doing most of all of the fix-up, there's still consistency issues with the labels themselves in order to get a good kind of learning signal. So, maybe we can learn something reasonably effective without requiring any of these kinds of manual labeling efforts, right? And if we go for some kind of unsupervised learning-based approach, just leveraging the information from these 3D reconstructions that we have. And in fact, you can actually go through and get a pretty nice understanding of, let's say, larger kind of furniture scale objects in these environments. This task here, because there are no labels, we don't actually predict any semantic labels. It's a class agnostic instance segmentation approach. So we predict instances, but not their individual semantic class labels here. And so the way this works is that we're adopting a self-training approach. So we first, from the reconstructed scans, try to generate some pseudo labels, pseudo masks for the instance segmentation task, and then go ahead and self-train on this kind of pseudo-generated data in a couple of iterative cycles in order to produce more informative masks here. So the quality kind of, in a sense, of these initially generated pseudo-masks is also pretty important, that we typically get more clean masks if sometimes, they might have multiple objects kind of aggregated together, or missing a mask on a particular object, but in general, the boundaries of these objects are more clean in this fashion. And the way that we get these pseudo masks is we go ahead and aggregate features from both the geometric signal that we have on the reconstruction and also the color signal. So this is features that are visualized on the reconstruction that are extracted from Dino, projected onto 3D, and a contrastive self-supervised learning approach for 3D features that's point contrastive in terms of how to supervise that representation learning without any semantic labels. And we can aggregate these features over geometric primitives on the actual 3D reconstruction, and then these primitives are just pre-computed with Feldman-Schwab segmentation that gives us a relatively low amount of primitives that we can then operate on top of. So aggregating these features together on top of these particular segments gets an initial signal in terms of which ones might be associated with each other. So that's what we're using here, basically taking a graph cut through these features on the segments in the particular scene, and that produces a bunch of initial proposals of masks of the objects here in the scene environment. And so it's of course not expected that these masks are perfect. As long as there's a sort of coherent signal across a large number of scenes that we generate in this kind of fashion, we can go through and learn to improve this signal. So here we have the initial mask generation, and then you can take your favorite sort of 3D architecture. In this case, we have a mask 3D based approach for the 3D backbone, and train it with these pseudo masks to produce output predictions. These output predictions we can then go ahead and incorporate along with the initial pseudomasks into a self-training iterative cycle where we go ahead and continue to output predictions and use them for training in order to produce the final output results here for the segmentation. So this continually improves. You can see from the initial reconstructed scan here, the pseudomasks that are generated are mostly too much clustering together of objects. But some of the objects do get separated correctly, and that signal can be leveraged in the self-training cycles in order to iteratively break down more and more accurate instance masks on this particular scene. And so this allows for a pretty nice instance segmentation from an unsupervised based approach. And here you can even get the chair and the table segmented pretty cleanly here compared to other kind of clustering-based or learning-based approaches for this kind of task. And so this, I think, shows that there's also a strong potential to get interesting signal out of 3D data without necessarily requiring the 3D labels, but it's still fairly coarse, the segmentations that we saw, right? So of course, the other approach for tackling this, when we look at some of the issues in terms of the semantic annotations on the original data set that we had, of course, the other approach that we can take here is to say, okay, let's just collect much higher fidelity data. And so this is the ScanNet++ data set that we've captured with much higher fidelity capture. And that also means that, in fact, the semantic annotation it's still reasonably expensive, but it's a lot easier actually to identify objects and to segment them out correctly when the geometry itself here, and this is about 1 millimeter accuracy of a laser scan, is actually much more accurate. And so you can see from these two very sort of similar scenes, the difference in the quality of the data capture here. And this is not only geometry, but of course, in terms of recognition and perception tasks, appearance is also very important signal. And that's something where we spent a bit of extra effort to make sure that we have a nice DSLR camera to capture images of these environments, as well as a commodity sensor, in this case, basically iPhone, that gives RGBD streams. So these are the different data modalities of the capture of these kinds of 3D environments. And what we're really aiming for here is some notion of high fidelity ground truth. So the reconstruction here is captured with a laser scan, and then we have the higher end color image sensor and a more commodity version of that sensor. And so this is the different scanners that we have. So the Faro scanner is capturing about 40 million points per scan, and that's somewhere around a millimeter in terms of the capture resolution. We have a Sony Alpha 7 that's our DSLR, and we have an iPhone 13 Pro that records an RGBD stream. So this data capture, we also, because we have manual camera trajectories for the DSLR and the iPhone, we also capture these in two different settings. So here you see the blue camera frustums are indicating the train capture trajectory. And then we also capture a bunch of test images. This is also potentially, for null view synthesis kind of applications, the test images are actually captured slightly outside of the trajectory of the train, so that you can really see about potentially synthesizing novel views and not ones that are within already an existing sort of trajectory of capture. So this is really aiming to benchmark not only things like geometric reconstruction, semantic understanding, but also how well does the appearance reconstruction work? And can you actually capture different views than those that were used in training? And of course, like I mentioned before, we also have some semantic annotations that are actually much cleaner in terms of the segmentation, because the object reconstructions are much more accurate here, as you can see with all these sort of small objects. And we get a very effective ground truth labeling from annotating all of the individual semantics here on these particular scenes. So to give a sense also of the DSLR capture, you can go ahead and generate a novel view synthesis output. This is from the Nerfacto library to just run a novel view synthesis on a particular reconstructed apartment kind of scene. And it looks pretty nice in terms of the fidelity because the ground truth capture of DSLR is pretty comprehensive here. And so overall, this is a data set that has 1,000 scenes. And we have 4 of those scenes, a bunch of DSLR captures totaling a little over 1 million frames, 10 million RGBD frames, and then also a bunch of individual unique class labels, as well as instances that are labeled across all of these particular scenes. So hopefully, maybe some of you guys are also interested in seeing what you can do with this kind of data set. We do have a few benchmarks that are set up here specifically for novel view synthesis and 3D semantic understanding. And with the novel view synthesis, I think one of the interesting aspects is this dual capture with DSLR and iPhone. They're all registered to laser scan. So you can go ahead and see how well the novel view synthesis from both kind of data modalities actually operates. So currently we have a benchmark that's on the DSLR frames. And this evaluates against these test camera captures that we have that are a bit outside of the train trajectory. And then we also have the 3D semantic segmentation and instance segmentation on the top 80 classes that have been annotated here on these scenes. And so these can also be evaluated on our benchmark website in terms of the semantic labels and also the instances here. So I think this is hopefully going to be interesting in terms of data signal that can be learned from pretty high fidelity ground truth. But of course, 1,000 scenes is still a pretty limited number if we talk about quantity. It's going to be several orders of magnitude off of these kinds of billions of samples. So we're still really operating under this kind of limited data regime if we want to learn these kinds of representations. So it would be nice, of course, to be able to distill this information from these sort of large text or image kind of models and propagate them down to the 3D learning process, right? And we can formulate this in a pretty simple kind of fashion to say, okay, well, let's learn our 3D features and then couple them directly to text features, right? So 3D, you have a pretty limited amount of potential data available and a lot of concepts that become difficult to learn because there aren't a lot of labels inherent in the 3D data set. But in a text encoding, you don't have this issue so much because the text model has seen most all concepts in this kind of setting. And so if we actually just tie the feature learning of the 3D features to a text encoder clip in this case, and then visualize that feature space, you actually get a much better structured space for semantic tasks. And this actually helps with both semantic and instance segmentation, especially in the low data regime with limited number of labels. So this is kind of interesting, but maybe we can actually leverage this for even stronger potential signals to get this, I say weak signal from text and image models. It's not weak except that it doesn't actually have spatial 3D information here, right? So weak in the sense of lack of spatial information, not in the sense of the representation capacity. And how can we inform this when we have very limited data, right? And the most sort of limited data settings that we have in this kind of domain tend to be for the high dimensional settings, right? So if we want to learn about interactions, there's very, very limited quantities. Thousands would even be, orders of magnitude larger than the amount of data that we have available for 3D interactions. So this is something where there's a lot of potential where if we can distill this information down from text or image models. And so this is something that we've tried to formulate here in a zero-shot approach. So zero-shot meaning that we don't train on any 3D interaction data. And here, given a text prompt in a scene, we try to generate that static interaction that captures that text description here. So the way that this operates is that because, quantities of 3D human scene interaction data are so limited, we rather try to get this information from image synthesis models. So latent diffusion, in this case, what we're using, has a very strong capacity to generate such potential interactions of humans with the environments. Of course, these are 2D images, right? So we try to distill this information into our problem setting, which is that we have a 3D scene that's been given, a text prompt of the interaction that we want to synthesize, and also an approximate point location in that scene where this should be synthesized. So we go ahead and distill this 2D interaction prior into a 3D synthesis. So the way that this works is, given this general kind of location in the scene, we want to go ahead and ask the image synthesis model to generate the interactions, right? So here we take that and render the location from a bunch of different views. And then we go ahead and do inpainting on these views in order to synthesize the human interaction that's been described by this particular text prompt. So we do have to be a little bit careful here. Of course, we have this 3D scene that's been rendered from a bunch of different views. If you ask an image model to just inpaint them all, there's a very high chance that it erases all of the background information of the scene and just resynthesizes something completely new. So we do need to do the inpainting in a mask where we think it's likely that a person would be there, right? So we find this by basically identifying the person token in the text. In this case, it's woman, and dynamically masking based off of the attention map associated with that particular token in the text prompt. And so this is what this looks like during the diffusion steps, and the masks that were used in order to generate these inpainted humans. So now we have a bunch of 2D interaction hypotheses that have been generated by this nice, image synthesis, image inpainting kind of approach. But of course, they've all been generated independently, which means that they're not going to be generally consistent with each other from a 3D perspective, right? So these are our 2D interaction hypotheses, and we want to figure out how to unify this information into 3D. So the idea here is basically pretty simple. We generate a bunch of hypotheses. In this scenario, you see 20 of them, because they're for sure not going to be consistent with each other. But if we abstract them out to just the human pose, some of them are probably going to be consistent with each other, right? Not all of them, but a small handful of them very well might be. So we abstract them first out to the 2D poses, because of course it's not easy to control the appearance of these people, that they are actually the same. And we use these poses in a robust optimization to figure out which ones are actually consistent with each other. So this is an optimization where we're solving for the 3D body model as its simple representation. So that's pose and shape. And it should project down to be consistent with these 2D poses, given that we have a weight attached to each particular pose that can be also optimized between 0 and 1. So this will tend to find the inliers that are consistent with each other in the optimization, and downweight everything else that's not consistent during this optimization process. And that allows us to lift this kind of information into a 3D synthesized interaction here. So that allows us to actually solve for view consistency. And so this is kind of, I think, pretty cool and powerful in various different ways, which is that now we don't rely on any sort of 3D interaction training and just on the capability of the 2D image model to synthesize these potential interactions. And that means that given a bunch of different kinds of scene environments, you can go ahead and generate various different kinds of interesting interactions here that are definitely, you know, not in any existing 3D human object data set. You can definitely also see some of the limitations as well of this kind of synthesis approach. Yeah, sorry, I don't know why PowerPoint's not capable of playing all of these 4 videos at the same time. But I guess you can see the general kind of interactions here. This abstraction into 2D poses in order to be able to find the 3D consistency in the interaction means that we have relatively coarse representations of interactions, right? If you look at the legs on this particular sitting sort of riding position, they're definitely not sort of as closely positioned as they probably should be. And that's because of this high level abstraction into something that's just approximately consistent as a 2D pose, right? Whereas if you actually had some formulation to bridge appearance in a more dense fashion, it might be an interesting way to get a bit more fine-grained kind of information in these kinds of settings. But I still think, you know, the generality here is very interesting. Of course, because of the formulation, we don't get really all of the finer-grained kind of details here. But I wanted to mention, you know, because we can actually leverage this sort of imaginative capability of large sort of vision language models, can we also then transfer this information to, let's say, like, you know, humanoid robots? So if we can synthesize, you know, a person potentially interacting with a given environment, can we, you know, use this information to inform what a robot might want to do, let's say a humanoid robot, so that we don't have to do too much transfer in terms of different modalities here. And so in this problem setting, we have a general kind of task description, fetch the laundry basket and the scene. This is in a simulated environment. And we want to produce a physically consistent trajectory here to, you know, comply with this kind of task. So this is a bit of an oversimplification because it's actually still a reasonably complex kind of task here. We not only take the high-level task as input, but we also take the high-level plan. So task is actually given as the breakdown of the basically sub goals that need to be performed in order to be able to achieve this task, which is lift the box from the floor, place the box on the floor, stand on the box, and then lift the laundry basket from the shelf. And so these are what we try to materialize given the RGBD images of the scene environment. So of course, we can then go ahead and take these prompts given information about this kind of scene and try to synthesize what this would look like, right? So if you ask, again, a latent diffusion model as the image synthesis here to synthesize lift the box from the floor, we get, in this case, a person lifting, you know, a box. And then we have placed the box onto the floor in this configuration, stand on the box, and lift the laundry basket from the shelf. So these are a bunch of images that are synthesized and that allow us to now perform a spatial reasoning. Okay, where should actually the contact regions be in order to be able to perform this task? And so that's the critical part we want to transfer from the synthesized images, right, which is to transfer the contact. So from the images, we can actually just do a human body estimation and identify where the hand regions are. And we can, again, just use an off-the-shelf model, not only for the human body estimation, but also for the monocular depth estimation. And then we can go ahead and leverage a 2D foundation model to generate, you know, features that might potentially correspond. So this is going to give us a bunch of potential samples that you see here that might actually correspond with each other in practice because the 2D foundation model has not necessarily been trained for this particular task where the identity of these objects are actually a bit different. We do actually have a bunch of potential outliers here, and so we do a sampling-based alignment for all of these potential hypotheses and then pick the best registration between the synthetic object and the estimated depth of the particular object in the image here. And that allows us to transfer the contact information from the hands from this image into the simulation scene environment here. And so then we can go ahead and try to perform this human to robot transfer, right? So this is the off-the-shelf estimated human of the particular point in time of the task and the contact points that we've transferred onto the synthetic version of the object. And then we can go ahead and formulate a trajectory optimization for the whole body of this humanoid robot that's guided with these 4 keyframes that have been determined for the main kind of steps that should be performed to fulfill this task. So this is optimizing for the robot locomotion, regularizing for collision penalties, collision-free trajectory, and then making sure that we are still abiding by the constraints of these particular keyframes. And so with that, that allows for solving for this particular optimization that lets us transfer this kind of information over. So this is the final output trajectory from the optimization. If we do a very naive kind of contract transfer to try to use this information, just use the correspondences from this big 2D foundation model, you get a bunch of unreliable kind of contact information that results in a relatively suboptimal kind of trajectory here in terms of the robot local manipulation that's being optimized for. So here we have just this kind of example in the simulation environment to try to give a sense of what we can potentially transfer over from this kind of 3D perception into materializing onto a robotic, a humanoid robot in order to perform these kind of particular tasks. So I think this is pretty interesting in the sense of learning in a limited data kind of regime, the different kinds of features that can be leveraged. This unsupervised kind of features are having, an interesting potential, but obviously, any kind of information that we can acquire from signal that we actually do have should actually be incorporated. It's not something that should be tackled in a fully unsupervised kind of setting. So we want to incorporate things like semantic or affordance priors that have been learned from this kind of very, very large scale, powerful signal, but weak in the spatial kind of information setting. There are a couple of clear kind of other directions that can be taken here, right? Which is that certainly, these powerful models, especially image and video generative ones, they operate in the appearance domain. So in order to probably make the most of this kind of distillation, it would be more effective to model appearance so that this information can actually bridge more effectively, and we don't have to go through these kinds of proxy information like human pose estimation in order to be able to try to bridge that signal. I mean, if you can do a more effective, let's say, differentiable rendering in order to optimize against this kind of output, it would probably be much more effective in a holistic fashion to model this kind of information. I'm also kind of interested in a bit more of a 3D synthesis kind of task. How can we use this kind of knowledge of interactions, especially for indoor scene kind of environments that we've been talking about? They've been built to support interactions, right? So if we can actually reason about these kinds of interactions, then maybe we can actually reason better about how to reconstruct high fidelity scenes from these kinds of observations, knowing that they need to actually support various kinds of potential interactions. So with that, I'd like to conclude and to thank my students and many of my collaborators who've done the work that I've been able to present here. I'm also happy to take some questions.
Yeah, thanks, Angela. Thanks a lot for the great talk. We don't. Yeah, I have a couple of questions. Just wondering, for example, for the semantic segmentation work which you shared, which is called Unseen, I think. And you were saying like there was this generated pseudo labels, and then there is a mask 3D. And I was just wondering, how good is the mask 3D performing on this task, and what would be the benefit of integrating this kind of pseudo labels? You show the benefit of having the pseudo labels, but somehow I'm not sure, like basically how much improvement one can expect by combining those two.
So I'm not sure if I got the question completely, but so when we train mask 3D with pseudo labels instead of, let's say, with ground truth supervision from annotations, we can get a performance that is sort of it's unfortunately it's kind of similar to a lot of other unsupervised approaches where performance is actually pretty reasonable. But if you are training fully supervised on the exact same task setting, that fully supervised information will allow for better performance. So I think here we're still limited by the number of scenes that we're using for training here, which is the original ScanNet dataset, whereas there's actually a lot of scene data now that has been released, like the new ARKit scenes has a lot of scene information that doesn't have full dense semantic information that might be interesting to actually leverage. So what's actually advantageous is to use this kind of approach and train it on a more limited data regime than having, let's say, 1,000 fully supervised annotations that are actually available, and then you can actually outperform these kinds of methods. The other sort of interesting perspective here in terms of using the unsupervised kind of training strategy, I think if you tie that in to the amount of data that you have available in, like, we didn't use the labels from ScanNet, but we could use them, and then in combination with large sort of scene data where we don't actually have dense labels like with ARKit, that's probably going to be the best performing kind of approach. But it is generally true that like a lot of interesting unsupervised methods, not only in the 3D domain, but also very much in the 2D domain, have a bit of a hard time competing fully with fully supervised methods in the exact same kind of data availability setting.
Thank you. Yeah, if we don't have any question, I have another one. So there is one?
Yeah, just
okay, please. Can you hear us?
Okay.
Yeah.
Hi, thank you for the great talk. I would have actually a question for regarding the part where you showed like this transfer from like you have certain instruction and then you're able to somehow like simulate like how a robot would interact with certain objects, right? For me, it's clear. Okay, like you do a 3D, like you generate the image with a latent diffusion, right? Then you generate like the pose of the human. But then how do you know exactly where how do you estimate the position of the object that you are interacting with, right? How do you estimate the 3D kind of like shape of this object that you're interacting with to understand where the interaction is happening?
Okay, yeah, so this is here, I guess. We generate this image, and then we'd run just an off-the-shelf pose estimation. This is WAM to estimate human pose. We also run an off-the-shelf monocular depth estimator, which is, I think, metric 3D. And then we go ahead and just do segmentation to identify the object and its particular depth. So this is like grounding dyno based segmentation in order to get, so here the depth information of that estimated, object in the scene. And then we go ahead and try to do this registration with the synthetic object that we have in the simulation environment where we have already the information about the 3D structure of that particular object given. And so that registration is then driven by this correspondence information from the 2D foundation model here. This is definitely a decently complex kind of process. Mostly the challenge is that the object that's been synthesized, it's very hard to control that it's actually, you know, the same object that you actually have here in the simulation environment. And, you know, maybe with more advances also in image synthesis, because they work on things like, you know, doing a bit of fine tuning in order to preserve identity of not just people, but objects that have been synthesized. Maybe that makes the problem a bit simpler. But this one is a bit finicky because of the identity change between the two objects in order to find the correspondences there.
And how do you transfer? So once you like the depth map and the segmentation, I guess you back project in 3D, and then how do you align?
Right, so we go ahead and take point locations in the image here, and then just compute, this is the heat map that's being visualized of using a pre-trained 2D model. You can imagine something like Dino. In fact, we actually use a model that's been specifically pre-trained for semantic correspondences. In order to, like, this heat map identifies which locations are likely to be correspondences from this particular pink key point here. It's often not super reliable. Like, it's a good way to sort of break down the whole image into potential regions of correspondence, because you also see, like, you know, these objects are decently symmetric, and so you get a lot of potential correspondence, left-right confusion, all this kind of stuff. And so between that, we go ahead and do a random sampling of all of these correspondences and take the one whose ICP error is the lowest, basically. And so that results in the actual pose estimation of the object to the one in the image. And that does also mean that for certain objects where you might have a very, very large change in identity, that the we're relying on sort of more contact-based regions. So sometimes this works, but it can also break if there's too big of a change in identity. Laundry baskets are mostly kind of the same looking, but there are certainly categories of objects where the identity of the object can change pretty wildly within the category.
Very interesting, thank you.
I have one online.
And go ahead, please.
Hi, thank you for the talk. I just wanted to ask, like, we have like many videos online which like kind of like we can use to estimate pose and do this kind of stuff, but why specifically we need image generation, or like why specifically this kind of workflow is important than just taking online videos of human working around and like estimate pose from them and do training. So like why it is.
So this is kind of interesting. I think if you're talking about sort of labeled data sets, let's say like, you know, video action data sets, there's definitely information there, but it's often captured in a slightly different kind of setting. So third-person videos are not that common. What appears to be much more common are like egocentric videos, but this is a bit challenging to transfer pose because you really only see the hands for the most part in an egocentric video. So then you need to solve this kind of problem of how do we infer the general human pose from only the egocentric view, which I think would be quite powerful because there's actually a fairly large data sets available of egocentric video around of people performing actions. The other videos that are available are much more limited, especially if you want something that is third-person view, so you can actually do a more reliable human pose estimation. And so maybe if you have a smart way to sort of filter through like video databases that are much larger, like YouTube or something like this, but you have a bit of a data filtering challenge there as well, because YouTube videos are very much in the wild videos, which means that, well, you might not get exactly what you're looking for in the search, and often these videos are actually captured for the sake of showing to other people. So they have things that are kind of annoying, like lots of cuts in the videos. It's not super clear how to do full, like, you know, pose estimation and all this kind of stuff on that kind of style of video. There's definitely other sort of data sets that are available that are a little bit more constrained. To my understanding, I think they're all relatively small. So there's like a cooking data set from the MPI from a while ago that has like third-person camera view, but this has only got like a few hundred sequences, and so you're constrained to that kind of cooking setting. So sort of these kind of general household tasks of like human object interactions can be a bit challenging because you're mostly limited to very specific kind of data sets. And ideally, for robotics, we would like a robot to be able to reasonably generalize, right, to a bunch of different kinds of settings. And that's one of the main sort of appealing factors of leveraging an image synthesis-based model, is because it's got pretty much these days the highest amount of generality that you could potentially imagine. Because it's been trained on effectively like internet scale level of data. It's actually, I mean, we've also realized that there are lots of things that image synthesis models also cannot synthesize. But it has much higher generality than the data sets that are currently available for training these kinds of tasks.
Okay, cool. Thank you.
Maybe one last question. So I'm just wondering, like, whenever it comes to interaction, actually there are a lot of details, but also it also involves some high level control and planning, right? Like in this case, you need to figure out where is the box, and then when you need to stand on it, and then to grasp the basket. And I was just wondering, what would be the suitable 3D representation? I assume like point cloud based representation would be too much fine-grained and too detailed. So what are your thoughts on it?
I mean, I think that involves two things, right? So one is that we take the plan as given here because we don't want to solve another very complicated problem which would need to be solved here. But I think other people have addressed this problem as well, which is this kind of task planning in robotics to break down a goal into a couple of more easily executed subtasks. And this is largely sort of LLM based as well, to my understanding, in terms of state of the art. So certainly it would be helpful to have more spatial information there. I think you're also talking about like what is the right 3D representation. And that's kind of interesting because I see there's currently, I mean, so to be honest, like for a long time, we have a lot of different kinds of 3D representations. And mostly, what's the best one just depends entirely on what's the downstream task you're actually looking for. So I think specifically with interactions, point clouds are also not great because they don't tell you anything really about collision. And so what I would hope for is that we actually do get like a real proper mesh-based representation. I think that is kind of challenging because what we have already learned through a history of lots of people studying these kinds of similar tasks is that sort of the more sort of you can propagate gradients through your 3D scene representation, the more effectively you can optimize. And that means that radiance field-based representations are actually extremely powerful. So anything that, uses like MLP or Gaussians or stuff like this for volumetric rendering formulations allows for gradients to be propagated effectively everywhere in the scene representation and not just on the surface. And so there's kind of this duality and tension between these kinds of representations. But I do think that will also make it very challenging in the end to transfer specifically to robotics-based kind of tasks, because maybe not all of them, but for some of them, you will need more fine-grained information, and radiance field volumetric optimization tends to lead to fuzzy geometric information. And that may or may not be sufficient information to then perform more fine-grained kind of tasks if you're not actually having a solid sense of the actual geometry that is available there. So I don't know what's the right one. Certainly I'm coming a bit more from a graphics perspective. So I have a bit of a fondness for some of the older graphics kind of representations, but I think in the end, whatever allows for the most effective optimization will probably win out there.
We have one more question in chat if you want. So we have one more question in chat. What are your thoughts on scalability of 2D generated images as supervision data, given that it still requires a lot of filtering and sampling? Would it help creating a carefully selected subset that's cleaner and more reliable for such humanoid robotics tasks, for example?
So I guess this is about generating sort of pseudo-label data from 2D synthesis, which is definitely complicated because it would require a lot of potential sort of curation, especially if we're talking about things like interactions. The 2D synthesis that I've seen so far does tend to fall towards certain kinds of modes. It might be like in an setting where we actually had access to very, very good sort of video generative models, that might be even more interesting here because you actually get some notion of motion. And part of the annoying part about using images for interaction kind of data is you get one sort of static snapshot of a keyframe, and it may or may not be the right actual keyframe that you want to represent that kind of action. So that part is very hard to control right now with image synthesis, and even generating a lot of them tends to fall on the same kind of general keyframe. So if you end up generating sort of the wrong keyframe for that interaction, it's very hard to generate the right one, even given infinite compute to resynthesize out of that image model. But I think if you can formulate your specific problem that you want to tackle in a clever way where you can actually use that synthesis and also the speed and compute of synthesizing at whatever scale you're interested in is feasible, it's still very interesting to potentially generate more general data here. Because typically when we talk about task settings where you have very, very limited data available, let's say, like 10 or 20 different kinds of locations, or maybe a few hundred sequences, like usually you have with 3D interaction kind of data. Some data is typically better than no data. So in that kind of setting, there's a lot of potential. When you start to move to task settings where you actually have more information available, then sorry, I think I'm echoing. Okay. Yeah. There's probably that general trade-off where you see the most effective output here when you're anyways operating on an extremely sparse amount of potential data, then to be able to even synthesize a limited amount more is can still provide a very strong signal, but there are definitely a lot of caveats.
Now there's audio, I think.
Okay, can you hear us?
Yeah.
Sorry, yeah, I was just saying thanks a lot for answering all the questions and also giving the great talk, and it's great to have you here today with us. And yeah, I hope everybody got quite a bit inspired from your talk, and then that's it for our theory for today. So thanks a lot, everyone. Thanks for joining, and see you next week, Friday. Take care, everyone. Bye-bye.
Thanks for having me.